This is our chapter 22 lecture on carbonyl alpha substitution reactions. So remember the way we designate the positions in carbonyl compounds. The carbon that's next to a carbonyl is the alpha position. So that's marked in our structure down here. We have C double bond O, and then the C next to that is the alpha carbon. So an alpha substitution reaction involves the substitution of an alpha hydrogen with an electrophile. So let's find those. All right, here's our carbonyl compound. Here's an alpha hydrogen, an H on the alpha carbon. In an alpha substitution reaction, that is replaced with something else, something that acts as an electrophile. The way this reaction works is by one of two intermediates. So there are two mechanisms in this chapter, really. And those intermediates could either be an enolate, which is a negatively charged compound. It has a resonance structure with a C minus and another with an O minus there. That enolate, the alpha carbon, attacks the electrophile, okay? And that's what makes the substitution. Or it can happen under neutral conditions with an enol. In that case, we have an OH attached to a CC double bond. The O electrons come in to make a double bond. That forces the CC double bond electrons to act as the nucleophile, attacking the electrophile that way. And then after a proton transfer, we end up with the same product. So enolate happens in basic conditions, and enol, intermediate, can happen in acidic or neutral conditions. Now, just as a quick little review here for probably will be handy for the final exam here, this can be a carbon-carbon bond forming reaction because the alpha carbon, the carbon next to a carbonyl, is a nucleophile. And we don't have an awful lot of carbon nucleophiles, but an alpha carbon next to a carbonyl is one of them. So here's just a quick review of the other carbon-carbon bond forming reactions we've seen so far. So our very first one in the first semester was where we make an alkyne out of an acetylide ion. Right, that's R C triple bond C minus. Right, C minus on the end of a double bond. And that's a nucleophile which can do SN2. So something like R C triple bond C CH3 or something like that, if we had methyl iodide or some other suitable nucleophile. Grignard reaction makes an alcohol, right? Like if I have acetone, that can be made into tert-butyl alcohol by addition of a methyl Grignard. That's essentially a C minus that comes and attacks the carbonyl carbon. Remember, the carbonyl carbon is electrophilic, the alpha carbon is nucleophilic. We can make a ketone with a Gilman reagent, right? If I have an acid halide, right, here's acetyl chloride, I can make that into something like acetone with a dimethyl copper lithium reagent. Or if I have an alpha beta unsaturated carbonyl compound, I can do a 1,4 addition, which removes the double bond and adds a new alkyl group to the beta carbon. We can make alkenes by the Wittig reaction. If I, again, take something like acetone, I can turn the C double bond O into a C double bond C with whatever else attached to it. We can make nitriles, and you don't usually think of that as a carbon-carbon forming reaction, but it is. If I had just some sort of simple alkyl halide, right, like 2-chloropropane, if I just react that with the cyanide ion, Cn minus, that'll just do an SN2 reaction, giving us this cyanide. But that did form a new carbon-carbon bond, and as we'll talk a little bit later on, we can change that nitrile into more useful things. So our alpha carbon reactions can fit into that. If I have something like acetone or something like that, if I, for instance, use a base, or we'll talk about reagents in a little bit, but we can do an alpha carbon substitution reaction where I'm adding on to that alpha carbon. Right? We can make a carbon-carbon bond. There are other things we can make, a carbon-halogen bond and so on. So that's what we'll be talking about